What's up, everyone? Welcome back to AI for Product Managers. I am Pranav. This is episode 15. So, in the last episode, you built a prototype. Today, we answered the obvious next question: how do you actually prove it works? Right? And this episode exists because the honest answer is not the way you are used to. So, let me tell you about the experiment that taught me this is the hard way. We ran a 2 week A/B test on an AI generated summary feature. Control was the old manual summary and the variant was the AI one. So the test came back with the variant winning on an engagement and p-value under 0.05. Everyone high-fived, we shipped it, and then the metric drifted back down over the following month. And then we dug in. The problem was not the feature, it was the test, because our variant was not the one thing. It was a slot machine. The AI produced a genuinely different summary every time it ran. So some were excellent, some were not. What we would measure was one particular fortnight's worth of lucky rolls, and we would mistaken that for a stable effect. So our p value was in the most polite possible terms, which is lying to us. So that's the whole idea behind this episode, and it's on the slide. In traditional testing, you compare A versus B. With AI, you are comparing A versus B random, a variant that has its own internal variance baked in. So blue button versus green button. So the green button is always green. AI summary versus manual summary. So the AI summary is different every single time. So here is what we are going. First, precisely why this breaks the math. Then the three types of variance because only one of them is the thing you are trying to measure. Then four approaches that actually work. And I'll tell you which to pick based on your traffic, then how to measure AI quality properly using LLMs as judge, and finally the pitfalls that will hand you a fake winner, right? And that's one a bit more technical than usual, but no math degrees required, I promise. Hit subscribe and let's get into it. Now, let's make this concrete because once you see it, you can't unsee it. Okay. The left side, a traditional test. Control is a blue line, always blue for every user on every visit. Variant is green, always green, so the same user gets an identical experience every time, right? So that's what deterministic means. And it's why the classic A/B testing works because the treatment never varies. And any difference you measure between the groups is the treatment, right? The maths gets to assume the only thing separating those groups is your change. So now the right side, your AI feature, the same user submits the same request twice and gets two different answers. So quality swings depending on the input. So it's brilliant on the easy cases and shaky on the weird ones. So the variant itself has variance living inside, right? So you are not measuring a fixed thing, you are measuring a moving target. So hence A versus B random. Okay. And here is why this matters more than it sounds. The red line at the bottom, the problem is not that your measured effect gets a bit smaller of or fuzzier. If it were just noise, you would get a non-significant result, right? Know and you'd know to keep digging it. And the actual danger is that this criteria variance can produce a result that looks clean and significant and is entirely fake. So your test says the AI variant wins P equals 0.03, and what actually happened is that during those 2 weeks that the AI happened to roll well, right? That's what happened to us. The stats were not wrong. They answered a different question than the one we thought we were asking to it, right? So the fix is not run it longer and hope. The fix is to understand exactly where the variance comes from and then deliberately design it out. So which is the next slide? Yeah, coming to the three kinds of variance, right? So this is the diagnosis. There are the three types of variance in an AI experiment, and able to name them is genuinely most of the battle. The number one, between group variance, this is control versus variant. The actual difference your change cost, this is the signal, and this is the only thing you are trying to measure. And in a traditional test, it's basically the only variance you will have to think about. Okay. And number two, within group variance. This is the new one, and it's the AI specific problem inside your variant group. The AI is producing different outputs for the same user and the same input. So your variant group's results are smeared out, right? That this is the noise. And critically, if you don't account for it in your simple size calculation, your confidence interval is too narrow and your p-value is overconfident. So that's the mechanism by which your test lies to you, not magic, just unmodeled variance, right? So number three is temporal variance, and this one is sneaky and specific to our era, right? So AI quality drifts over time. The provider silently updates the model, and someone on your team tweaks the prompt mid-experiment. So usage patterns shift. This is confounding, right? Meaning it's a change that tangled up with your treatment, so you genuinely cannot tell whether your variant improved or whether GPT just had a good week, right? And I want to be blunt. If someone edits the prompt in week two of your experiment is over, not damaged, over, start again. And this time freeze the prompt and pin the model version as well. So the whole job on the bottom line, isolate number one while actively suppressing two and three. So every single approach I'm about to show you is just a different tactic of doing that. So let's go through them. Approach one and two, and these are the opposites philosophies. Approach 1 says, let's overwhelm the noise with data. Approach 2 says, let's just delete the noise. So, approach 1, the bigger sample, it's brute force and it's honest. And where a traditional test needs about 1,000 users per group over 1 to 2 weeks, an AI feature test needs 5 to 10,000 per group over 3 to 4 weeks. Your confidence target does not change, still 95%. You just need far more data to get there because you are paying for that extra within group variance, right? The rule of thumb here is plan for 3 to 5 times a normal test. This works beautifully if you are a high traffic product. It fails completely if you are a early stage with modest traffic, right? Or if you need an answer this month itself. And honestly, most teams watching this are in that second bucket, okay? Which is why approach two is my default, okay? And approach two, pin the output. Instead of accepting the randomness, you remove it. Method A, set a fixed random speed per user, so a given user always gets the same AI output. So suddenly your variant holds still and it behaves like a normal A/B test. All your existing statistical instincts work again. And method B, even more aggressive, pre-generate every output in advance and serve them statically, right? So zero live variance. Now the trade-off, and I want to be straight with you about it. You lose the live AI experience, and more importantly, you will not catch real world variance, right? You are deliberately testing a best case, frozen version of your feature. So, what you learn is, does this idea work when the AI behaves consistently? Which is genuinely the right first question, but you will need a follow-up to check what happens when it's live and wobbling, right? Here is the practical guidance. Pinning is where I would start for almost everyone because it gets you a clean answer fast and cheap. So there is also a smaller bonus, pinning per user session. Stop the genuinely confusing experience where a user refreshes the page and their answer changes underneath them. So which is a UX problem and a data problem. Okay. Coming to approach 3 and 4, these are the clever ones. Approach 3, the multi-armed bandit. Instead of locking traffic at a 50-50 split for 4 weeks, the split adapts. Week 1, it's 50-50. As evidence accumulates that B is better, the algorithm shifts the traffic 60%, then 70%, then 90. So it continuously reallocating toward whatever is winning. Okay. So why is this especially good for AI? Three reasons. It handles high variance gracefully because it's built to make decisions under uncertainty rather than assuming a fixed effect. It minimizes how many users ever get exposed to the worse arm, right? Which really matters when worse might mean a bad AI answer to a real customer, and it converges faster than a fixed split. Okay, so the cost is that the clean, simple, like here is my p-value, story gets uh, murkier, and some stakeholders find that uncomfortable, right? Worth it in my view, but know that going in. Okay. Approach 4 is interleaving, and this is the most elegant technique on the slide. Instead of splitting users, you split the results. Same user, same session, and you mix outputs from both models into one list. Position 1 from model A, position 2 from model B, alternating, then you watch which ones they click, right? And the reason is this is so powerful, it completely eliminates between user noise. In a normal A/B test, a big chunk of your variance is just that different people behave differently. So here it's the same person in the same moment with the same intent, choosing between your two options, right? It's a direct preference measurement, and it needs dramatically less traffic, often 10 times less. If you are comparing two models or two prompts on a search or recommendation surface, this is the best tool on the slide, full stop. Okay. The catch is it only works where you have a ranked list of multiple slots to fill. You can't interleave a single chart answer. So there is only one slot. So bandit for general feature tests under uncertainty, interleaving whenever you have a list, right? And pinning when you just need a clean, cheap read. Okay. Now, right. So the measurement, because choosing the approach is only half of it, you have to decide what you are actually looking at. And with AI, you need four layers, not one. Layer one is business metrics, revenue, retention, NPS, Net Promoter Score, support cost down 20%. This is what your executive cares about, right? And it's what gets you funded. And layer two is product metrics, task completion, satisfaction, resolution rates above 70%. This is whether the feature actually works for users. And the layer three is AI quality, accuracy, relevance, safety, hallucination rate under 5%. And layer four is technical, latency, cost, throughput, P95 under 2 seconds. Because a brilliant answer nobody waits for is a broken feature. Also, watch cost because per token pricing means a successful feature can become an expensive one at a scale, right? So now the red line is because this is the single most important sentence in this episode. An AI variant can win on your business metrics while hallucinating more. Okay, so let that sit for a second. Engagement is up, so your primary metric says ship it, but your hallucination rate quietly went from 3% to 8%, and you didn't measure that. You shipped a feature that confidently lies to 5% more of your customers, right? Sometimes those things are casually linked. A confident, fluent, wrong answer can be more engaging than a hedged current one, right? Optimizing purely for engagement can actively select for confident nonsense. Okay, so which is why layer 3 metrics are guardrails and guardrails have V2 power. This is not a scorecard where you average everything out. If the hallucination rate breaches your threshold, the variant loses, right? No matter how good the business number looks. Decide those thresholds before you start. So write them down and hold the line when the pressure comes. Okay. Now, so how do you actually score AI quality at a scale? Because accuracy above 85% sounds great until you realize somebody has to judge thousands of outputs. Human evaluation on the left is the gold standard and it stays a gold standard always, right? Humans catch nonce, tones, sarcasm, cultural context, all the things that actually matter and that models are weakest at, right? So you typically use a 5-point scale across a few dimensions: accuracy, helpfulness, safety, but it's slow and genuinely expensive. Hours of a real person's time per batch. So you are realistically doing 1 to 500 evaluations. That's the right tool for the high stakes final catch. And LLM as judge on the right is a technique that makes this practical. So you use a strong model like GPT-4 or Cloud to grade your features output. You prompt it with the criteria and it scores them. It's fast, it's pennies, right? And you can do thousands in 1 hour. Okay, so now you can evaluate 10,000 outputs instead of 100. Okay, and the number that matters is the roughly 80% agreement with human judges. Think carefully about what 80% means. It's more than good enough to steer you to compare two prompts, spot a registration, pre-filter the obvious failures. It's not good enough to be the sole basis of a for a ship decision, right? Because that remaining 20% tends to be exactly the subtle high stakes cases you care most about, and there is a known bias. LLM judges LLM judges to tend to prefer longer, right? More confident, more fluent answers, which is not the same thing as more correct. Okay, so the answer is both in a specific order. Use LLMs as judge as your wide net across thousands of outputs during rapid iteration. Then use human evaluation on the sample that actually decides whether you ship. And the one step people skip on the green line is calibrate the judge first. Take 100 outputs, have humans score them, have your LLMs judge, score the same 100 and compare. If they agree, great. You can trust the judge at scale. If they don't, fix your judge prompt before you rely on it. Otherwise, you are just scaling up a measurement you have never verified it. Okay. Now, let's make this practical because four approaches and four metric layers can feel like a lot. Here is how I actually choose. Question one: which of two prompts is better? Use a multi-armed bandit. Prompt comparisons are noisy and you are genuinely uncertain, right? Which is exactly the situation bandits were designed for. And you limit how many users see the weaker prompt. And question two: should we upgrade from one model to the newer one? Interleaving every time you are comparing two versions of the same thing on the same surface. So let users tell you directly with their clicks. Needs far less traffic and gives you a much cleaner preference signal. And question three: does adding AI help at all versus no AI? Here you do want to classic fixed split with a big sample, okay? Because this is a genuinely casual question about the concept itself, and you want the clean, boring, defensible answer. Yet it cost you 3 to 5 times the traffic, right? That's the price of real answer to a big question. And question four: what confidence threshold should trigger escalation to a human? Pin the outputs and sweep the threshold. Pinning removes the AI's randomness so you can isolate the one variable you can actually care about, the threshold, right? This is a great example of why pinning is useful. You are not testing the AI, you are testing a decision rule about the AI. And then the green line, which is for most of you, honestly, if you don't have the traffic for any of this, and plenty of good teams do not run an underpowered A/B test and pretend. Okay, an underpowered test is worse than no test because it gives you false confidence with a number attached. Instead, pin your outputs, take 100 real cases, and have humans evaluate them properly. That's not a consolation prize for an early stage product, that is genuinely the highest quality signal available to you. And it takes an afternoon for you. Okay. Now the honest part, 5 ways your AI experiment will lie to you. I have made most of these mistakes personally. So one is like running too short. A week is almost never enough to clear AI variance, right? 3 weeks minimum, and that's not me being precious, because it's because you need enough data to see through the noise and enough time to catch the temporal drift. The second one is ignoring within group variance in your sample size calculation. This is the technical one that actually caused my bad ship. If your stats don't account for the fact that the variant itself varies, your confidence interval comes out too narrow and your p-value is overconfident. So your test will declare significant that that is not there, right? If you have a data scientist, this is the exact sentence to go and say to them. Three, testing too many variants. Every arm you add dilutes your sample, right? And you already need 3 to 5 times the traffic. 3 arms maximum, and honestly, two is better. Okay. So four, no guardrail metrics. We covered it, and it can win on engagement while hallucinating more. And five is changing the model or prompt mid-test. Someone just improves the prompt in week two with genuinely good intentions and silently ends your experiment. So pin your model versions explicitly and tell your team the prompt is frozen while the test runs. So say it out loud in the stand-up, okay? And on the right is your pre-fight checklist, like 7 boxes, and I would genuinely tick these on paper before you launch anything. Hypothesis and AI quality metric, right, written down, right? Sample size that accounts for variance, output spin per session, guardrail set including cost, model and prompt version frozen, at least 3 weeks on the calendar, and the approach you choose with a written reason why. because in 4 weeks, when someone questions the result, the sentence is what saves you. Okay. So 10 minutes of this checklist prevents the thing that happened to me, shipping with confidence, then quietly watching the metric drift back. Okay. Now I want to give you one mental model to carry out of this episode, because the four approaches are easy to forget and this sentence is not. You are not comparing A versus B. You are comparing A versus B random, right? And everything we covered today is just a different strategy for dealing with that one set of parentheses. And you can sort every technique into three buckets. Bucket one is remove the random, pin the seed, pre-generate outputs, freeze your model, and prompt version. You are eliminating the variance so your normal statistics work again. And bucket 2, outlast the random, 3 to 5 times the sample size. So 3 plus weeks of runtime, bandit allocation. You are accepting the variance and gathering enough data to see through it. Bucket 3 is like sidestep the random, right? Interleaving same user comparison. Human evaluation on 100 cases. You are restructuring the question so the variance stops mattering. Okay. So remove it, outlast it, or sidestep it. So that's the whole episode. And when you are planning your next AI experiment, that's the first decision to make. So before sample sizes, before metrics, which of those three I am doing and why, right? The line at the bottom is the version of this I would tattoo on a whiteboard. AI finds the pattern, but you design the experiment that can actually see it, right? The intelligence is cheap now. Rigorous measurement of that intelligence is the skill, and it's yours. Okay, fine. Let's lock it in. Let's cite the four approaches in one breath. One bigger sample, 3 to 5 times the traffic if you're lucky enough to have it. Two, pin the output for a fast, clean read. That's my default and where I would start. Three is multi-armed bandit when you are uncertain and you want to limit how many users see the worse arm. Four is interleaving when you have whenever you have got a ranked list, right? Because it's the cheapest clean signal there. And underneath all of it, measure all four layers: business, product, AI quality, and technical, with your AI quality metrics holding V2 power. And your homework is 3 steps. One, pick one AI feature, either something already in production or the prototype you built last episode. Two is write a one-page experiment plan, hypothesis, primary metric, approach, sample size, and guardrails on one page, not 10. Like if you can't fit in one page, you haven't decided it, right? And three is the step I actually care most about. Name your variance strategy out loud. Are you removing the randomness, outlasting it, or sidestepping it? If you can answer the questions in one sentence, you are already designing better experiments than most teams shipping AI right now. And here is an experiment I'd love you to run because it's genuinely eye-opening. 5 minutes. Take an AI feature you already have and send it the exact same inputs in 10 times and line up the 10 outputs side by side. Most people are quietly shocked on how much they differ. The spread you are looking at is your within group variance, right? It stops being an abstract statistical concept and becomes a thing you can see. So do that before you plan your next test. So drop a comment and tell me the trickiest AI experiments you have had to design. I read every one, and the messy real world cases are my favorite, right? So next episode is 16 is the prompt engineering masterclass, like 5 components and how to build a prompt library your team actually versions like code, because everything we have done in this phase, like the reset synthesis, the prioritization, the prototype, the experiments, all of it runs on prompts, right? Time to master them properly. So subscribe, ring the bell. I am Pranav. This has been AI for Product Managers, and I'll see you in episode 16. Peace. Thank you.